Today in class we spent time reviewing division and re-expressing a polynomial function as the quotient times the divisor. And tonight we're going to review that process, talk about the remainder theorem and the factor theorem, and then also review factoring, so that tomorrow during class we'll spend our time practicing all of the different factoring methods. Okay, so we'll start right in with the remainder theorem, and the remainder theorem says that if you have some polynomial function p of x and it's divided by a linear divisor, then the remainder r is p of a. Okay, and so we're going to go ahead and take a look at an example. We're going to use synthetic division, so I'll review that because it's fast and we have a linear binomial divisor. So we have our p of x and we have our divisor. We're going to take the 3 and we'll put it in the little box, and then we'll put the coefficients of the polynomial p of x. So 1, -3, 1, -3. The constant goes to the right of the t. We're going to always bring down the first coefficient, and the reason for that is because technically it's like dividing x cubed by x, and we know that the answer will be 1x squared. Okay, so we'll bring down that 1, and then we go through the process of multiplying. 3 times 1, answer goes here. Then we're going to go ahead and combine those two numbers. We have a 0. Multiply, combine, multiply, and combine. Now the purpose of our box, we said, is so that the remainder will always be in this position, and so obviously this is evenly divisible because there's no remainder. So my quotient in this particular example is going to be 1 degree less than the dividend because we're dividing by a linear, so x cubed divided by x is going to give us 1x squared, plus 0x, which we will not write in, and then plus 1. Okay, so our next question is, what's p of 3? So that means, what's the value of the function p of x when x equals 3? Okay, and so you go through the process. 3 cubed, of course, is 27. And then 3 squared is 9, and 9 times 3 is 27. And so what we have is 27 minus 27 and 3 minus 3. So we have an answer of 0. Okay, and then we're going to switch gears for a second, but you'll notice that p of 3 is 0. That's important. All right, could the results of the division from the first part be used to write p of x as the product of x minus 3 and another polynomial? And this was following up from the classwork from today. So p of x can be re-expressed as the divisor times the quotient. Okay. So you could write out the whole thing, p of x, so you could in fact write x cubed minus 3x squared plus x minus 3 equals. Now, based on our work for number 1 and number 2, what can you conclude about x minus a if you know that p of a equals 0? So here we evaluated p of 3, and we got an answer of 0, and we found p of x divided by x minus 3 came out with no remainder. So what can we conclude? We can conclude that if p of a equals 0, then x minus a is a factor of p of x, because this indicates that it's evenly divisible. This will be our remainder, and so if the remainder is 0, then we know that p of x is evenly divisible by x minus a. Or in our specific example, that p of x, x cubed minus 3x squared plus x minus 3 was evenly divisible by x minus 3. Okay, I'd like you to go ahead and stop the video for just a moment and explain why you think that x minus 1 must be a factor of x to the 6th minus 1. And I'm going to ask you to try to use this idea of the remainder theorem. Okay, welcome back. We are going to go ahead and talk about what's called the factor theorem. And factor theorem and remainder theorem are usually talked about together because they have a lot of information in common. So for any polynomial p of x, x minus a is a factor of p of x if and only if p of a equals 0. So that's kind of this idea that the remainder theorem, we said if a polynomial function is divided by x minus a, then the remainder is p of a. Here we're saying in order for it to be a factor, the remainder has to be 0. Okay, I'm going to ask you to go ahead and stop the video again and complete example 1, letter A. Determine whether x minus 2 is a factor of p of x, and you can do that couple of different ways, but I'm going to ask you to try to do it using the idea of the remainder theorem. Okay, welcome back. We're going to talk about example 2. And for example 2, you have a word problem, and you have an illustration given with it. We're talking about the volume of a rectangular prism. So volume, of course, would be the length times the width times the height. And it's modeled by this function v of x. It says identify the values of x for which v of x equals 0 and use the graph to factor v of x. Okay, so if we look at the graph, we're looking for where v of x equals 0 or where the function equals 0. Okay, which means that's where your y value is 0, so where it crosses the x-axis. Okay, and it looks like it crosses right here at x equals 1, and it touches or crosses here at x equals 3. We're going to assume drawn to scale. And then it looks like we have one more point of intersection at x equals 4. And we could double check each of those by subbing in x equals 1 or v of 1 and making sure that it's 0. And we can sub in v of 3 to make sure it's 0. And we can sub in v of 4 to make sure that that is also 0 to prove that they are factors. Okay. So if those are true, then we can go ahead and factor this by working backwards. If we know that x equals 1 is a 0 or a solution, and x equals 3 and x equals 4, then we can work backwards to re-express. So we have x minus 1, x minus 3, and x minus 4. If we're saying that each of those equals 0, we can now say that v of x in factored form is equal to this. Tomorrow during class, we'll go ahead and verify this. So we'll put in the original equation, and then we'll go ahead and put in our factored form, and we'll verify that these two equations are in fact the same, or that they're onto each other.